Okay, so in this video, we're going to look at two additional series tests, the telescoping series test and the p-series test. Now, they're not really very closely related to each other, but they do both have polynomials in the denominator. What's different is that the p-series test is actually much simpler, and we will look at the integral test in the next video, which we will be able to use to prove that the p-series test works the way that it does. But we want to look at the telescoping series test first. The telescoping series test is somewhat complicated. I personally always forgot that it existed and would forget to check it when I was first learning how to do this. But the telescoping series test is a way of taking essentially a rational expression that has factors in the denominator, factors that differ by an integer or several integers, but they're integer steps apart, and applying partial fractions to them so that we can see how the terms are kind of partially canceling each other out as they go. The telescoping series test is powerful because it allows us to actually find the limit of the sequence, which a lot of our other tests actually aren't able to do. But they can only say whether they converge or diverge. But here, if it converges, we can actually say what the limit is. And so it's very powerful, but it does require a fair amount of algebra. So what we're looking for in order to apply the telescoping series test is we are looking for factors in the denominator that are separated by whole integers. So n and n plus 1, or n and n plus 2, for example, or n plus 1 and n plus 2, n plus 1 and n plus 3, etc. You can also do, like if they're they're two values apart, but you have like 2n plus 1 and 2n plus 3. In that will actually work, because when n is 1, in the one case, you will get the same value for the second factor as you would if you let n equal 2 in the other factor. So they're going to have the same kind of behavior. What you can't have is like n and 2n plus 1. That's not going to work. But as long as you have similar coefficients and they're differing by like one whole step, so 2n plus 1, if you jump up by 2, that multiplier of 2 in front of the n, 2n plus 3, that's going to be a pair that you can use. If you had, for instance, 3n plus 1, you would need 3n plus 4 to go with it, because that would be 3 bumps up, so that when n changed, the other one would also match it with one different value of n. So that's sort of what you're looking for when you want to apply a telescoping series test. You're looking for a denominator that is either already factored or which can be factored into these factors which have integer spaces apart. Now, in order to do that separating, you're going to need to use partial fractions. And I have another video on partial fractions elsewhere in this playlist that you can look at for that. It's also in the algebra playlist. And there's one additional thing that you need when you split up a telescoping series like this, is not only do the denominators have to be 1 unit apart, the numerators have to be the same. So if you're doing partial fractions on one of these things, and you think, oh, this might work for telescoping series, but in one of them you get a 2, and the other one you get a 3 or something like that, and you get a 1/2 and a 2/3, that's not going to work. They have to be the same size. They can both be a half or they can both be 1, because you can always pull out the common factor, but the numerators have to be the same. Otherwise, the canceling is not going to work, and then you should use a different test. So let's look at this particular example. For this first one, I've actually already split it up into my 2 terms, and so I've done the arithmetic for it just so we can see how these factors, these denominators that are differing by 1 integer, are going to work and cancel each other out. So let's look at the first couple of terms. So if I start with n equals 1, I'm going to get 1/2 for this one, and then 1/3 for this one. If I start with n equal 2, then I'm going to get 1/3 and 1/4. And then if I plug in n equals 3, I'm going to get 1/4 and 1/5. And then if n equals 4, I'm going to get 1/5 and 1/6, and so on. And so what you can see is if you move the parentheses around and you start regrouping things, this 1/3, this negative 1/3 from the first n equals 1 is going to cancel with the positive 1/3 from when n equals 2 from the first fraction. And then the negative 1/4 is going to cancel with the positive 1/4. And the negative 1/5 is going to cancel with the positive 1/5. And so what's ending up happening is that the first term, because these are one step apart, the first term from the first fraction survives, but then everything in the middle cancels until you get to the last term that you're calculating. And whatever that last term is, like if you're thinking of the partial sums, whatever that last term is, that's your sum. The first fraction you got, and then the last one. So the first term from the sequence, the first fraction, the first term of the first term, basically, and the last term of the last term. So if you're doing an infinite sequence, this last term is going to be the limit of that last term. And again, the denominator here, n plus 1, n plus 2, doesn't really matter. It's going to be the limit of that term as n goes to infinity. And since that goes to 0, the sum is going to go to a half, because we keep adding and subtracting these differences on, and everything gets canceled except till whatever that last term is, and the last term is 0. Now, even though algebraically it is true that you could, in theory, separate these out, the reason that we do them together is because there's more power in determining how they behave together than there is in determining them separately, because separately these both diverge, and infinity minus infinity is undetermined. It could converge or it might diverge. And so if we do them collectively together, we can see how they will cancel and we can actually get the limit. So again, even though this is theoretically possible, it actually won't be helpful in the case of a telescoping series. Now here's another example. And in this example, these are now 3 terms apart. And again, this numerator was chosen so that when we use partial fractions, we can split it up into 1 over n minus 1 over n plus 3. Now, if we start plugging in terms, we're going to see that this is a little bit more complicated than the previous one, but there is a method to this madness. So again, if I start with n equals 1, I get 1 over 1 and then 1 over 4. And then plug in n equals 2, I get 1/2 and then 1 over 5. And if I plug in n equals 3, I get 1/3, and 3 plus 3 is 1 over 6. And so on and so forth, 1/4 and 1/7, 1/5 and 1/8, 1/6 and 1/9, and so on. Now, you'll notice that the 1 doesn't have a counterpart anywhere, and neither does the half or the 1/3. But when you get to the 1/4, there was a minus 1/4 up here. So there's the first 3 terms, the first 3 pieces that we get from this first fraction, those don't have anything to cancel them. But then things start canceling. So negative 1/4 and positive 1/4, and negative 1/5 and positive 1/5, and negative 1/6 and positive 1/6. And then when we get to the end of our list, then things stop canceling. There's no more, we haven't gone far enough to list any terms that will cancel for these. So it's the last 3 terms in the sequence that we have to worry about. So the first 3 terms get included in our sum, the first 3 pieces from the first fraction, and then the second fraction, we need the limit as those 3 copies of those terms go to 0, as n goes to infinity. If they go to 0, then the sequence will converge, the series will converge. And if they don't go to 0, then it will diverge, that end behavior. So if I call my first component B1, that 1 over n plus 1 essentially, and then 1 over n plus 2. So I'm all those things that don't cancel the first three terms. Here, 1 over 1, 1 over 2, and 1 over 3. And then I'm subtracting, because these are all negative terms out here, the last term, the term right before that, and the term right before that. So again, how you exactly, you can put these as n plus 3, n plus 2, n plus 1, that's fine. The behavior that in the limit is not going to matter as you go to infinity, whether you're counting them as n plus 3s or n minus 1s or whatever. Infinity minus 1 is still infinity. And so each of these pieces, the limit is going to be 0. And so the sum of the series is just going to be these first three pieces that didn't cancel. So this is the way that we actually see this behavior. If your factors differ by 1, then you have just the first component and the last component that you have to worry about. The first component when n is 1, and the limit as n goes to infinity for that second piece. If you have 2 steps apart, then you would need the first 2 values for that first part of your pair, your difference, and then the limit for the last 2 parts. And then, again, 2 copies of it. If you have 3 steps apart, as we had in this case, then you add up that first positive version with n equals 1, n equals 2, n equals 3, and then you take the limit of 3 copies, essentially, of the last term. The denominator is differing by 1 in this case, and then you let n go to infinity, and that's going to be your infinite sum. Now, you can also have examples that diverge. For instance, if you had log n over n plus 1, you could split that into log n minus log n plus 1, and then you would be able to calculate the terms all along the way, but that last term, as the limit goes to, as n goes to infinity, the limit goes to infinity. And so even though you're adding and subtracting things, you're still going to end up diverging because you're adding and subtracting things that are getting bigger, not adding and subtracting things that are actually getting smaller. Now, the second one that we're going to look at in this video is the p-series test. And the p-series test is very easy, particularly compared to the telescoping series test. Now, the p-series is essentially like the harmonic series. It has 1 over n, but it's 1 over n to some power. The harmonic series is in fact itself just with p equal 1 in this case. Now, essentially what the p-series tells us, and again, we can prove this with the integral test, which is in the next video, but what the p-series tells us is that if this p-value is 1 or smaller, then the series will diverge. But if p is 1 or bigger, then the series will convert. If it's bigger, strictly bigger than 1, the series will converge. And part of the reason for this, and we'll see this when we do the integral test, is that if you apply the integral test to this general formula, what you end up getting is that you either get log, which goes to infinity when p is 1, and you get a positive power in your numerator when p is less than 1. But if you start out with p bigger than 1, then you will still have your infinity will be still in the denominator when you do your limit. And so everything will converge very nicely. So let's just look at an example here. Here, you don't even actually have to use the p-series test for this. 1 over n to the negative 1/2 is equivalent to the square root of n. And this is actually very easy to see that the terms are getting larger. And so this will diverge. We could use the nth term test for this, or we can just say, okay, this power of n in the denominator is less than 1, less than or equal to 1, and therefore it will diverge. When p is in between 1 and 0, you will still, the terms will be going to zero. So the nth term test will no longer apply, but you would actually be able you can actually establish, again, using the integral test in the next video, you would be able to show that, in fact, those series, even though the terms are going to zero, they fail to converge. They are not decreasing quickly enough. On the other hand, when you get for values bigger than 1, like let's say n equals 2, p equals 2, then these do converge quickly enough, and the p series, we can then say this in fact does converge. There are examples where we have combinations of alternating series with these p series tests, and you don't even have to use the p series test if it's alternating, because the alternating series will take care of both these cases and the sort of in-between cases where they will not converge when they're all positive, but they will converge when they alternate. The p-series test is very useful, but we don't often end up with series that are this simple. This test will become most useful when we talk about comparison tests, because the comparison tests will deal with series that are much more complicated in terms of their form, but they, in the limit, behave like a p-series, and then we can use them as a point of the p-series as a point of comparison. So we'll be able to say the p-series we're comparing it to converges by this test, and then that will imply something else by comparing it with something that's a little bit more complicated. But that too is in a later video.